Hello everyone. In this session, we will review the contents of week 1. So you can see that these contents are in week 1. That means we have to know what is complex number, how to deal with complex numbers algebra, what is Argand diagram, complex plane disk, and how to compute the powers of any complex number, how to find the roots of an equation where complex number is involved. So these things will be found in week 1. So the most important parts from here is how to compute powers, how to find roots, complex plane disk, okay? And besides this, you have to know another important thing, that is what is the difference between argument and principal argument. So argument of Z, principal argument of Z. So you can think about this session as the continuation of these previous two sessions. Okay, because we are going to solve some problems directly from the reference book. So you already know that any complex number is written in this form, that is Z equals x plus yi, where x and y both are real numbers. So the form that you can see from here is known as rectangular form or Cartesian form of complex number. Similarly, we have a polar form of complex number, that is z equals r e power I theta. So here r is the modulus and theta is the argument of z. So you can see that I have written argument with small a, small letter a. So there is a difference between argument of z and argument of z. So be careful about the letters. That is, here we have small a and here we have capital A. So any argument can be written as theta. So this one is also written as theta. But just to clear the difference between argument and principal argument, this one is known as principal argument. So just to have the knowledge of principal argument, so you can use two different forms, that is small a and capital A. So let's say this is theta and this is big theta. So this is how we can differentiate these two. So we know how to convert rectangular form to polar form and from polar to rectangular. So now, besides this, we also have to know the definition of principal argument. So you already know that argument is like the angle. Okay, so angle from positive x-axis. I am coming to that part. But what is principal argument? Principal argument is a unique value. That means principal argument can be only one value. But this argument, it is of multiple values. That means it can take several values. Okay, we can take several values for argument. But argument, that is principal argument, is only a unique value. Principal argument has a domain, that is, it is in between minus 180 degree to 180 degree. or equal to 180 degree. So you can mention this one as principal argument of Z, that is capital A. So principal argument is in between minus 180 degree to 180 degree or equal to 180 degree. So if we use radian form, then we can write minus pi to plus pi. Okay. So this is the definition of principal argument. So now argument, it can take multiple values. It can take several values. That means it can be 0 degree, it can be 180 degree, it can be 360 degree, it can be 270 degree, it can be 150 degree. Okay. Or we can think about 60.5 degree. These are positive values. We can also think about negative values, negative 30 degree, negative 45 degree, negative 180.5 degree. So principal argument can take only one value in between minus 180 degree to 180 degree or equal to 180 degree. But this argument is a form where we can take several values. So you will understand this one if you have a look on in the geometrical concept of complex number, that is z equals x plus yi. So where we have a complex number like z equals x plus yi, we can think about a point. That is, complex number is nothing but a point x comma y. So you know how to locate a point in xy plane. So let's say this is x and this is y. So we have the point x comma y. But remember, here x and y are real numbers. I is the imaginary unit whose values can be root over negative 1. So I equals root over negative 1. So this y-axis is the imaginary axis, and this x-axis is the real axis. So this is the only difference between the previous course with this course, that is in math 110 or 120. You are familiar with xy plane where x is real axis, y is also the real axis, but here y axis is imaginary axis. So we have located the point. Let's say this is x comma y. X comma y can be in first quadrant, second quadrant, third quadrant, fourth quadrant, depending on the point that we are choosing. So complex number can be a point, and we can think about complex number as a vector. So we can also direct it from the origin O to the point. So this is how we can think about complex number. So this distance is x and this is y. So this is how we can describe the rectangular form of complex number. Now the polar form, that if the distance from origin to the point is denoted by r, that is the modulus. So if we use the Pythagoras theorem, that is, we know that r squared equals x squared plus y squared. So definitely r equals root over x squared plus y squared. Okay, so since r is the distance, so we can just keep the plus sign here. And also from positive x-axis, this is the positive x-axis, this is the negative x-axis. So from positive x-axis to the direction, that is positive x-axis to the line, there is an angle. So that angle can be found by this way. We know that the definition of tan theta is y over x, that is perpendicular by base. So using this form, we can find tan inverse y over x. So this is how we can find r and theta. That means we have the polar form r and theta. So besides this, you can also recall the two alternative forms. That is, what is x? X equals r cosine theta, y equals r sine theta. Okay, so by these four relations, these two and this one, we can easily convert the rectangular form to polar form or from polar to rectangular. So the angle that I have found here, that is theta equals tan inverse y over x, this is known as this argument. So this is not the principal argument. So we have to be sure about the principal argument, because principal argument can be in between minus 180 degree to plus 180 degree or equal to plus 180 degree. So this argument is always directed from the positive x-axis to the line. Okay, so a point can be in second quadrant, let's say here. So the distance from origin to the point x comma y is r, and from positive x-axis to the line it will be theta. Similarly, um, you can have a point on third quadrant. This is the angle theta, and this is r. Similarly, we may have a point in fourth quadrant. So from positive x-axis to the line, we'll get the theta, and this distance is r. So here we can think about another form, that is, suppose we have a point in first quadrant. So we can easily find r, we can easily find theta. Now we can easily understand that, let's say this angle lies in between 0 degree to 90 degree. We can easily think about where the point is located. Okay, it is in between 0 to 90 degree. That means the value can be 45 degree, let's say. So whenever we are coming from positive x-axis with 45 degree angle, we are getting this line. So we can extend our idea, that is, we can come from 360 degree plus 45 degree, then we are getting the same line. We can think about another rotation. So 360 degree plus same angle, we are getting the same line. So we can think about that this theta is not a single value, it can take several values. So theta plus 2 pi, we are getting the same line. If we come another 360 degree rotation, then it will be theta plus 4 pi. So this is how we can describe theta. That means theta equals theta plus 2k pi. So this is how we can think about just the argument. So argument can take several values. So not only in this orientation, this is called positive orientation, we can think about also in negative direction. That is, suppose we have a point here, so we can come from this negative orientation. Okay, so again we can think about theta equals theta negative 2 pi, theta negative 4 pi. So that is theta equals theta plus 2 negative k pi. That means theta minus 2k pi. So now we can generalize the idea, that is, k can be positive, k can be negative. So theta equals theta plus 2k pi, where k equals 0, plus minus 1, plus minus 2. Now, you are wondering that how I am writing 2k pi. That is, whenever we are making one rotation, then we have theta plus 2 times 1 times pi. That is here k equals 1. When we are making second rotation, so theta plus 2 times 2 times pi, that means this is the value of k. So 2k pi, 2k pi. That's why I have written 2k pi. So now you can understand that the angle can take multiple values. So small a rg of z is theta plus 2k pi, where k is 0 to plus minus 1 plus minus 2 up to infinity. So this concept is very important for all the upcoming contents. So the details can be found in these two lectures. So I suggest you to go through these two lectures. You will get the entire idea. Okay. And now let's recall another two forms. That is, we have the Euler identity. Euler identity is e power I theta equals cosine theta plus I sine theta. We have another identity, that is e power minus I theta equals cosine theta minus I sine theta. We have de Moivre's theorem. Okay, that is, if we have cosine theta plus I sine theta with power n, then what we can write? That is, we can write cosine n theta plus I sine n theta. That means this power is coming in the position of the angle. So with theta, this n can be multiplied. So this is what we know as de Moivre's theorem. So these are the things that you have in week 1. So let's recall all the things again. That is, the rectangular form is z equals x plus yi, polar form r e power I theta. So since we have understood that e power I theta is cosine theta plus I sine theta, so we can write r cosine theta plus I sine theta. So this is what we can write. So this form and this form, both these forms are known as polar, and this one is rectangular. So this is the first form, that is known as polar form. It is also the form which is the second form. So since we have here exponential term, so this is called exponential form of complex number. And since here we have sine theta and cosine theta, that is trigonometric. So we can write it is trigonometric form of complex number. So let's solve some problems directly from book. So you can see that the content that you have here, complex numbers algebra. So here, let's solve some problems. Let's say this one. We are going to add or sum two complex numbers, and we want to take the geometrical figure from this. Okay, so let's say we are adding 2 plus 3i plus 4 minus 5i. So first of all, you can see that 2 plus 3i is a complex number. We can write it is 2 comma 3. That means in Argand diagram, we can easily look at the point 1 2 1 2 3. That is 2 3 will be here. So complex number is always directed from origin. 4 5, 4 minus 5, 1 2 3 4. The point will be 4 minus 5, minus 1 minus 2 minus 3 minus 4 minus 5. So this is the point that is 4 minus 5. It is in fourth quadrant and the first one is in first quadrant. So what will be the summation? Summation will be 2 plus 3i plus 4 minus 5i. We can sum up the real parts. 2 plus 4 plus 3i minus 5i. So real parts have been grouped and the imaginary parts are combined together. So we have 6 plus 6, let's say minus, it will be 2i. So we have finally the summation, that is 2 plus 3i plus 4 minus 5i is 6 negative 2i. So we are dealing with complex numbers. The answer that we have found, the result is also a complex number. So this is also a point, 6 comma minus 2. So geometrically, addition of two complex numbers follow the parallelogram theorem. That is, the diagonal of a parallelogram will be the summation of the two vectors. That means, let us look at this point, that is 6 negative 2, 1 2 3 4 5 6 minus 1 minus 2. So the point is here, 6 negative 2. This is our result, that is summation. We can say from the concept of vector, we can say this is the resultant vector. So you can see that we have found our result and the geometrical interpretation is complete. But if we think about an imaginary line, let's say we have another line here, so it is forming a parallelogram, okay, and the result that we have found, it is like the diagonal of the parallelogram. So that means addition will always give you the parallelogram form. Okay, so this is how we can deal with 61. Okay, these problems. Now let's solve some other problems that we have here. 63. I have already mentioned that the details can be found in these two lectures. Okay, so we are going to solve some problems directly from this book. So here I have mentioned that the modulus R is equal to x squared plus y squared square root. So if we have a complex number z equals x plus yi, then R equals root over x squared plus y squared. This is known to us. Okay, but since this is the modulus of z, so we can also think about this one as modulus of the complex number z. So R equals z. That means R equals this one. So modulus of z equals also root over x squared plus y squared. That means you can understand that this part is the real part, this part is the imaginary part. If we try to find out the real part of z, it will be x. What will be the imaginary part of z? It will be y, because y is adjacent with the imaginary unit I. So this is the imaginary unit I, and the imaginary part of z is y. So remember that x and y are coming from real numbers. So Re of z, that means real part of z. Im of z, that is imaginary part of z. So we can extend our idea, that is R equals modulus of z equals x squared. That means real part squared plus y squared. That means imaginary part squared. So real part of z, that is x squared plus y squared. We are just replacing x and y with re and im. So please try to note down this thing. And the angle that we have found so far, that is theta equals tan inverse y over x. So sometimes you have to correct the answer that you are going to find. So depending on the location, if a point is in the first quadrant, then you don't need to add or subtract anything. The result that you are getting from this one, this formula, that is okay. But if the point is in the second quadrant, then you have to correct something. You have to add or subtract with some quantity. If a point is in third quadrant, then again you have to correct the result that you are having from this formula. That means the formula that you have, that is tan inverse y over x, will not give you the correct answer. So sometimes you have to adjust the answer, okay, based on the location of the point. Similarly, if we have a point on the fourth quadrant, you have to adjust the angle, okay. So for first quadrant, you don't need to have any tension. Use this formula, you will get the result. For second quadrant, there may be some options. For third quadrant and fourth quadrant, you need to adjust. So let's solve some problems from here. You can see that z1 equals 4 negative 3i, z2 equals minus 1 plus 2i. That means we have to solve these problems. So let us solve the first one, that is z1, z2. We have to find z1 plus z2 modulus. So if we add z1, z2, so it will be 4 negative 3i plus negative 1 plus 2i. So that means 4 negative 3i negative 1 plus 2i. That means we have 4 negative 1 plus negative 3i plus 2i. So that is 3 negative I. That means if we try to locate the first point z1, it is 4 negative 3. That is 1, 2, 3, 4. 1, 2, 3, negative 3. So this point is here. Negative 1, positive 2. That is negative 1, positive 2. Negative 1, 1, 2. The point is here. It is Z2, it is Z1. So we can think about a parallelogram. So obviously, you can easily understand that we have the result 3 minus I. It is also a point 3 negative 1. So 3 negative 1 will be here. That means the result is here. So this is the parallelogram where the diagonal is acting as the summation. Okay. So this is how we can find the summation or subtraction. Now, we still have to do something, that is, we need to find the modulus of z1 plus z2. So since we have found the modulus, that is, we have found the result z1 plus z2. So let us find z1 plus z2 modulus. So it means that, let's say, we are calling the answer as big Z. That is, for our better understanding, we are thinking that Z1 plus Z2 is the big Z. So that is Z. So where Z equals 3 minus I. So you can easily understand that Z equals 3 negative I. So comparing with the standard form, we have 3 plus negative 1 I. So what is the value of X? This is X plus Y I. This is Y. So that is X equals 3, Y equals negative 1. That means square root of x squared plus y squared. So square root of real part is squared plus imaginary part is squared. That is 3 squared, negative 1 squared. That is, we are getting root over 9 plus 1, root over 10. So this is our modulus R. That is modulus of Z1 plus Z2. So we have found the result. This is how we can find the modulus. So geometrically, the result that we have found, modulus of Z1 plus Z2, that is root 10, is this one, the distance from origin to the point. Okay, so let's solve another problem from the same part. Okay. So let us solve C. So you can see that we have Z1 bar, Z2 bar. So now, besides all the definitions, we need to know another definition, that is, what is Z bar of Z? If Z is a complex number, x plus yi, then Z bar is known as the conjugate of Z. That is, it will be x negative yi. Just y, previously it is plus, now it will be minus y. This is the change. So again, if we think about, we have modulus of Z bar, it will be square root of x squared plus negative y squared. So we have x squared plus y squared. That means we can think about modulus of z. So you can see that modulus of z equals modulus of z bar. That means the modulus for the main complex number is equal to the modulus of the conjugate. Okay. Similarly, we can draw another conclusion. If we have z bar and we need to find z bar, that is, it will be x plus yi. We will get the same thing. So you will get to know everything if you have a lot of practice. So let us solve this one. That is, we have z1 bar and z2 bar, and we need to find the subtraction. So what is z1? Z1 equals 4 minus 3i. So we need to find z1 bar, that is conjugate of z1. It will be 4 plus 3i. Previously it is minus 3i. Now it will be plus 3i. That means whenever you are going to find the conjugate, remember that we have to just change the sign of y. If it is minus, then plus. If it is plus y, then it will be minus y. Similarly, we have z2. Z2 equals negative 1 plus 2i. So z2 bar will be negative 1, negative 2i. Remember, there will be no change in x. X is just like the previous one, but we are changing the sign of y. So this is the definition of conjugate complex number. Now we have to subtract z1 minus z1 bar minus z2 bar. So this is very easy. Z1 bar minus z2 bar, that is 4 plus 3i. This is z1 bar. Negative z2 bar is minus 1 minus 2i. Okay, so we can find the subtraction easily. 4 plus 3i, negative negative it will be positive, negative negative it will be positive. So we have 4 plus 1 plus 3i plus 2i, that is 5 plus 5i. So this is the subtraction, that is z1 bar negative z2 bar. So this is how we can deal with the complex number algebra. Okay, let's solve some other problems from the reference book. I will share in Discord which problems you have to solve. Okay, you can see that we have to describe and graph the locus represented by each of the following. So let us take the first one. This is another formation. Uh, it is like complex plane disk. What is Argand diagram? The xy plane that we are working on, where x is real axis and y is imaginary axis, is known as Argand diagram. The mathematician Jean Robert Argand. Okay, so based on Argand diagram, we can plot anything that we have in our hand. That is, if we have a complex number, we can think about a point, and then we can easily plot that point in Argand plane. Here, try to understand the concept, that is, we have to describe and graph the locus represented by each of the following. So locus means the path that the equation has. Okay, it may be a circle, it may be ellipse, it may be straight line. Okay, that means any geometrical figure can be found from this equation where complex number is involved. So let us solve the first one. That is, here we have modulus of z negative I equals 2. So to solve these problems, you have to follow some steps. Where you have z, you know that z equals x plus yi, because we are going to find the equation. Based on that equation, we can think out, yeah, that is a circle, or this is an ellipse, it is a parabola, it may be a straight line. So everything will be based on the equation. So for finding the equation, we need to have x and y. So that's why we are plugging z as x plus yi. So that means modulus of x plus yi negative I. That means we just have replaced z by x plus yi. So now we can do some simple algebra, that is, we can group the real part and we can group the imaginary part. So since we have I in this part and here, so we are grouping these two. Now this is another complex number where we have this form, that is real part plus imaginary part with I. That means we have modulus of real part plus imaginary part I. So what we can write, in order to remove the modulus sign, you know that in order to remove the modulus sign, you know, we can write by this modulus of z equals square root of real part squared, imaginary part squared. So this part is important, that it can be written as x squared plus y minus 1 squared. That means, let me write in easy form, real part squared plus imaginary part squared equals 2. So what is the real part? Real part is x. So x squared. Imaginary part is only y minus 1 squared, not I, just y minus 1. Okay. So now we have square root of x squared plus y minus 1 squared equals 2. So we can take square on both sides. So that means we are getting x squared plus y minus 1 squared equals 4. That means 4 can also be written as 2 squared. So we have found one equation from the equation that we have where complex number z is involved. From this equation we have found another new equation. That means the previous equation and the final equation are same, but the representation is different. That is, it is with z and I, but here we have x and y form. So we can compare this equation with our renowned form that we know, that is, it is x minus 0 squared plus y minus 1 squared equals 2 squared, which is one equation of circle, that is x minus ax squared plus y minus k squared equals r squared. So center of the circle is k, ace is 0 and k is 1. What is the radius? Radius r equals 2. That means we can easily draw the geometrical figure. So that is what we have to find, that is describe and graph. So we have already described by this method. Okay. And finally, we are going to draw the graph. So now we are sure that this is nothing but a circle. So to draw the circle, we need to locate the point where the center is, that is 0 1. So 0 1, this is the center. Radius is 2. So from the center we can think about 1 2, here 1 2 1 2 1 2. Now we can easily draw the circle. So this is our circle. Okay, that means the equation represented by modulus of z minus I equals to is a circle. So there are some problems in next section, that is the same concepts are with less than, equal or greater than. Okay, so it may be less than, it may be greater than, it may be less than equal, it may be greater than equal. But the problems that you have in 1.71, these are with equal sign. So concept is same, but whenever you are going to draw the equation, then you need to have some concept. So since we have modulus of z minus I equals 2, we can easily think about this circle. So from the same problem, I am trying to describe all the concepts, that is with less than equal, greater than equal. So you will get the idea. That is, we may have, let's say we have modulus of z minus I equals 2. So we are sure that this is a circle. It is with this circle. Okay, if we have the same equation, modulus of z minus I equals 2. Okay, let's say instead of equal we have less than. That means from the very beginning you have less than. So where you have less equal, then replace it by less than. So this is the change that you have to do. Okay. So finally, we will have the equation like this one. We will have x minus 0 squared plus y minus 1 squared. Instead of equal, we will have less than 2 squared. So it is still a circle, but the region is different. So we are drawing the same circle because the equation is same. So this is our circle. Since we have now less than, be careful, we don't have equal. So since we have less than, that means we have to shade the interior portion. This is the shading. Okay. Be careful also, that is, the shade will not touch the circumference because we don't have equal. So whenever we have equal sign, it means we are on the boundary. We are on the circumference. This is the region that we have here. This is known as locus. So what is the locus of the second one? It is the interior portion. Similarly, if we have the same type of problem with, let's say, this time we have equal, less than equal. So finally we will get less than equal. So this time for less than, you can easily see that we have the interior, but since we have also equal, so the shading or region will touch the boundary also. That means we have the full interior part. That means less than or equal means interior, and on interior region and the boundary. So let's say we have the same problem with now greater than. Greater than 2 squared, greater than 2. That is, we have modulus of z minus I greater than 2. So this time, since we have greater than, we have the exterior boundary. That means this portion is denoting that this is the circumference and the radius is 2. So greater than means we have the exterior. So the region that we have, it is here. So this concept is important for the upcoming contents. So please try to remember that region of complex number is a vital factor. So now let's think about another form. Suppose this time we have greater than with equal sign. So since we have greater than, the exterior region will be here, and since we have also equal, so the lines will also touch the boundary or circumference of the circle. Okay, so greater than equal means exterior and on the boundary. Okay, so this is how we can deal with this type of inequalities. Less than, greater than, these are called inequalities. Similarly, we have another equation here. This is with equal sign, and finally you have to show that with some algebra, by algebraic manipulation, you will reach to one equation that will denote the equation of ellipse. You know that equations of ellipse are x squared by a squared plus y squared by b squared equals 1. So concept is same. First input x plus yi, where you have z. So this problem is similar. Now let us come to the next problem, that is how to find the powers or roots of any complex number. So let's say we have we have this equation. So we need to solve this equation. We have z power 6 plus 1 equals root over 3i. So here the question is solve the following problem. So if we have to solve the equation, first we have to think about how many solutions we will have finally. So you can see that if we solve this equation, then there will be solutions or roots. Solutions are also called roots. So we will get finally the roots of z. Okay, so that means how many solutions we will have? That is, we will have 6 solution. Let's say z0, z1, z2, z3, z4, z5. So there will be 6 solution. 1, 2, 3, 4, 5, 6. Just think about x squared plus 5x plus 6 equals 0. We will have 2 solutions depending on the highest power of x. So similarly, we have here a equation where we have complex number z. So z power 6, that means you will have 6 solutions. So you can go through these 2 lectures. You will get the idea what I'm going to solve here. Okay, so I'm going to solve this one directly. First of all, what you have to do, you have to set this number on the right side. It will be -1 plus root over 3i. Okay, now you can see that we have z power 6 equals -1 plus root over 3i. So if we just want to keep z in left side, it will be -1 plus root over 3i power 1 over 6. So I hope you have understood up to this one. So that means we have z equals -1 plus root over 3i power 1 over 6. Okay, so we have a complex number inside this parenthesis. That means we have a complex number. Let's say this is another complex number which can be denoted by w1. So -1 plus root over 3i. We are not taking the whole quantity. 1 over 6 is not taken here. Okay, we have just taken the inside quantity, -1 plus 3i. So now what you have to do, you have to convert this rectangular form. It is in rectangular form, that is x plus yi. The standard form is x plus yi. So this number is in rectangular form. So we have to convert this in polar form. R e power I theta, and we have 1 over 6. So how to convert this one to polar form? We know that we have to find R. So R equals square root of x squared plus y squared, that is minus 1 squared plus root over 3 squared. So we have 1 plus 3, that is square root of 4. That means R equals 2. So we have found R, that is R equals 2. E power I theta. So what will be theta? So we can find argument, that is theta equals tan inverse y over x. So tan inverse y, y is root over 3 and x is negative 1. So we have tan inverse negative root over 3. So tan inverse negative root over 3 will be negative 60 degree. Okay, that means argument of z, that is this argument, is negative 60 degree. You can remember that argument, that is small a arg, can be any values. So it can take multiple values. But I have also mentioned that depending on the location of a point, you have to adjust the argument. Whenever I have started the session, I have mentioned that the point can be in first quadrant, can be in second quadrant, can be in third quadrant, can be in fourth quadrant. If the point is in first quadrant, then there is no chance. If we have the point in third quadrant and fourth quadrant, or even in second quadrant, then the formula tan inverse y over x, okay, the result that we are getting from this formula, that needs to be adjusted. Okay, so let us adjust the angle, but at first we have to think about the location of the point. So what is the point? Negative 1 plus root over 3i. This one, I am talking about this one. So let us locate the point. Any complex number is a point, so it is negative 1 root over 3. So negative 1 root over 3 means it is negative 1, and root over 3 is 1.73 something, so it will be like here. So you can see that we have found the location of the point. It is negative 1. Oh, there is a mistake here. We have positive root over 3, right? Positive root over 3. So it is 1, it is root 3. So negative 1, let's say this is root 3. So we have here. So negative 1, positive root over 3. So any complex number can be detected from origin. So this is in second quadrant. So we can easily find the modulus R that we have already found. R is 2. What is the angle or argument? Argument is always from positive x-axis. So you can see that by our first view, we can understand that it is in between 90 degree to 180 degree. Okay? But whatever we have found from this portion, it is negative 60 degree. So negative 60 degree is on the backward portion. Okay. So that means to have this amount of theta, what we have to do? We can easily see that our argument will be in between 90 degree to 180 degree. But whatever we have found, that is not correct. We have to adjust. Okay. So what we have to do? Argument of z, that is theta, will be what? Can anyone say?
Sir, 120 degree.
120 degree. That means the total angle is 180 degree. Okay.
Yes, sir. Minus 60 degree.
So to get just this one, we have minus 60 degree to add. Okay. So now the argument of z, that is theta, equals 120 degree. From here we are getting. So now we can understand that 180 degree, yeah, this is 180 degree. What we have assumed, that is okay. So now let's get back to our work. We need to find all the solutions. So so we just need to input now the angle theta, that is 180 degree. So it will be 180, sorry, 120 degree. It is 120 degree. So we can just replace it by 120 degree. But it is wise to work with radian. So we know that 1 degree equals pi over 180 radian. So 120 degree is equal to 120 pi over 180. So that means we have
2 pi by 3.
2 pi by 3. Okay, so that is theta equals 2 pi over 3. That means our point is here. So this angle is 120 degree, that is 2 pi over 3. So I hope you can remember that argument can take several values. If we add again 2 pi, we will get the same line. If we add again 2 pi, that is total 4 pi, we will get the same line. That means whatever rotations with 360 degree we are making, we are getting the same line. We can come up from positive direction or negative direction. So that is theta is equal to theta plus 2k pi, where k equals 0 plus minus 1 plus minus 2, like that. So that is small arg of z can be theta plus 2k pi. This is the broader sense. So let us plug theta at first. Theta is 2 pi over 3. So now to have all the solutions, already we have found one solution. We have z. Z equals something. But the problem is here, that is, if we keep our solution like that, that is, we have found our solution z. So if we leave our work up to here, then we are losing another 5 solutions. So we have just one solution up to now. So to have all the solutions, what we can do, we can use this formula. That is where we have the argument theta. Let us plug that with theta plus 2k pi. That means z equals to e power I. We have the portion theta 2 pi over 3. So theta plus 2k pi. So this is the thing that you have to do. So what I have done here, I have just replaced theta with theta plus 2k pi. Okay, that means where we have theta, we are using theta plus 2k pi. That is, argument of z should be replaced by theta plus 2k pi. So since we have introduced k here, so instead of z, we can also write zk. Now we can think about k equals 0, k equals 1, k equals 2, like that. So we can do some simple calculation here. 2 e power I 3, so 2 pi plus it is 6 k pi 1 over 6. So you know that if we have ab power m, then we can write a power m, b power m. So we have two things multiplied, that is 2 and this one. So what we can write, zk equals 2 power m, so m is 1 over 6 times e power 2 pi plus 6k pi over 3 with power 1 over 6. We are using this formula. So again, you know that if we have e power m power n, then we can write e power mn. So we can write 2 power 1 over 6 times e power I. So this is m, this is n. It will be 3 times 6, that is 18, 2 pi plus 6 k pi. Or let us write in a clear way, that is times this e power m power n, e power m n. So now zk equals 2 power 1 over 6 times e power I 18, 2 pi plus 6k pi. So finally, we have found all the solutions. Okay, so now we can have all the solutions that we have to find. We need to have 6 solutions. So we can mention that k can be 0, can be plus 1, can be plus minus 2, like that. So this is our input now. For the first solution, k equals 0. Let us take k equals 0. So let z0 equals 2 power 1 over 6 e power I 2 pi. If we multiply 0 with this, it will be 0. So we have 2 power 1 over 6 e power I, that is 2 pi over 18. That means directly we can write pi over 9. Okay, so this is our z naught. This is our first solution. So this solution is in polar form. We have r e power I theta. So every solution is also a complex number. So we know that if we have z equals r e power I theta, so using Euler's identity, we can also convert that to rectangular form. We know that e power I theta is cosine theta plus I sine theta. So we have r cosine theta plus I r sine theta. So if we compute cosine 9 pi by 9 and sine pi by 9, you will get a decimal value. That means you will get x plus y I finally. So from here we can also find the rectangular, we can also find the polar form, okay, if we want. Let us input k equals 1. So z1 will be 2 power 1 over 6 e power I 2 pi plus 6 times 1 times pi, that is 6 pi by 18. So we have 2 power 1 over 6 e power I 8 pi over 18. We can also simplify this one. So this is Z1. Similarly, for K2, we will have Z2. For K3, we will have Z3. For K4, we may have Z4. And for K5, okay, we will have Z5. That means when we have K equals 2, we are getting Z2, K equals 3, we have Z3, K equals 4, Z4, K equals 5, we have Z5. That means Z0, Z1, Z2, Z3, Z4, Z5, total 6 solutions are in our hand. So this is how we can think about the computation of roots of any equation. So this problem and this problem is same, that is find the cube roots of this one. It will be minus 11 minus 2i power 1 over 3. So first we can consider z equals this. That means we are starting from this portion. If we have a equation, if we have an equation like this, we are converting that equation in this way, complex number with a power 1 over 6. Similarly, we have a complex number with a power 1 over 3. So this is how we can easily compute the roots of any equation where complex number is involved. So sometimes we have to look at the solutions, that is Z0, Z1, Z2, Z3, Z4 in Argand diagram. So all the solutions will have the same radius, because every time we have the same radius 2 power 1 over 6. You can see 2 power 1 over 6. So 2 power 1 over 6 is a decimal value. So let's say we have a circle with radius 2 power 1 over 6. So the solutions that we have, all these solutions lie in the circumference. Let's say this is Z0, this is Z1, this is Z2, this is Z3. Let's say this is Z4, this is Z5, like that. Okay, all the solutions will be in the circumference of a circle with radius this. Okay, you can check. You can check with your own problems. Okay, you will get the idea. Okay, so besides this, we have one part that need to be done, that is how to find the powers. Up to now we have talked about roots. Now let us think about powers of a complex number. Let us take a problem. Suppose we have a problem 1 plus I with power 7. So if we have 1 plus I squared, we can easily apply a plus b squared formula, that is a squared plus 2ab plus b squared. This is easily done. But if we have higher power, then what we can do? So first, the concept is just same like finding roots. Whatever we have done here, we have found the rectangular form first, and then from rectangular we have found the polar form, that is we have found r and theta. So that is what we have to do again here. So we have the point, the inside point is z equals 1 plus I. Let us consider this is w. So w equals 1 plus I. It is in rectangular form x plus yi, where x equals 1, y equals 1. So r will be root over x squared plus y squared, that is root over 1 squared plus 1 squared, that is square root of 2. So r is 2. At the same time, what is the argument? So tan inverse y over x, that is tan inverse 1 over 1. So tan inverse 1, that is theta equals arctan of 1, it is 45 degree. So argument of z equals 45 degree, that is theta equals 45 degree. So 45 degree is pi over 4 radian. So let us solve this. We have found the polar form. So polar form of this will be r e power I theta power 7. So r is square root of 2, yeah, and theta is pi over 4. So one thing I need to mention here, that is this time we are using the same formula, theta equals tan inverse y over x, and the result that we have found pi over 4. So is it accurate or we need to adjust? So this is accurate one, because the point 1 plus I, it is 1 comma 1, it is in first quadrant. So that's why the angle is looking like it is in between 0 to 90 degree, and we have found 45 degree. So that's why I have mentioned earlier that if we have a point in first quadrant, the point is in first quadrant, so this formula will give us the accurate angle. So we don't need to adjust this one, we don't need to add or something. Okay, we don't need to add or subtract something. That is what I want to say. So the angle that we have found, it is okay. So root over 2 e power I theta is pi over 4 power 7. So root over 2 power 7 times e power I pi over 4 power 7. How I have written this? Just like the same formula. If we have ab power m, a power m, b power m. So let us consider this is a and this is b. So a power m, b power m. And again we have the same concept, e power mn, that is e power m times n. So root over 2 power 7 times e power I pi over 4. 7 will be multiplied. So this is how we can solve this problem. Now it is our power 1 plus I power 7. We are done. But if you wish to find the rectangular form, then you can also find. How? Let us solve this one also. So it will be root over 2 power 7 e power I theta. So that means using Euler's identity, it will be cosine theta plus I sine theta. So that means we can now write root over 2 power 7 cosine 7 pi over 4 plus I root over 2 power 7 sine 7 pi over 4. So that means you can see that the whole thing is x plus I y. So any complex number can be written in rectangular form. Okay. So we can also find the decimal value if we want, because cosine 7 pi over 4 will take a decimal value. Always work with radian and then multiply root over 2 power 7. You will get, let's say, something plus I root over 2 power 7 with sine 7 pi over 4. So this is what we can understand from this concept. Okay. One important thing I need to mention, then all the things will be covered. That is how to find the standard form of complex number if we have a rational form. Let's say we have 1 plus I, and let's say we have 1 negative 2I. Okay, so we need to find the standard form. Let's say we are looking for x plus yi form. So it is in division form. We have learned how to sum up two complex numbers z1 plus z2. We have learned how to subtract z1 minus z2. And this time we are going to learn how to divide z1 by z2. So at the same time, we will also know how to multiply z1 and z2. So if we have a division form, we can't direct divide this. So in that case, whatever number you have in denominator, think about its conjugate. So 1 negative 2i, its conjugate will be 1 plus 2i. That means it is z2. Z2 bar will be 1 plus 2i. So we have 1 negative 2i multiply with 1 plus 2i. In upper part, we have 1 plus I. So multiply with 1 plus 2i. That means now if we cancel this and this, we are getting the same previous thing. Now it's easy to calculate. So 1 plus I, 1 plus 2i. 1 minus 2i, 1 plus 2i. So 1 minus 2i, 1 plus 2i. It is just like a plus b into a minus b. That is a squared minus b squared. Okay. So a plus b, a minus b, a squared minus b squared. And here what we are getting, that is we can multiply 1 plus I with 1 plus 2i plus 2i squared. So we have 1 negative 4i squared in the denominator. In upper part, we have 1 plus I plus 2i minus 2, because I squared is minus 1. So you must know that I is root over minus 1. I squared will be minus 1. I cube is I squared times I, that is minus 1 times I. So I cubed equals minus I. I to the 4 is I squared times I squared, that is minus 1 minus 1. So minus 1 times minus 1 will be 1. So I to the 4 is plus 1. So minus 1 times minus 1, it is plus 1. So this is how we can compute the powers of I. So that's why it is minus. So we have 1 negative 2. We are grouping the real parts. We are also grouping the imaginary parts. That means we have done multiplication. Now we are doing the addition. So I plus 2i. Similarly, in denominator we have 4i squared, that is minus 1. So now we have in upper part 1 minus 2, that is minus 1, plus I plus 2i, it is 3i. In denominator we have 1 plus 4, minus times minus 1, it is plus. So we have minus 1 plus 3i over 4i. So this is our result, but it is not in standard form. Our standard form will be x plus yi. We need to have x separately and y separately. So what we can do, we can just write by this way: minus 1 plus 5, sorry, minus 1 over 5 plus 3i over 5, that is minus 1 over 5 plus 3 over 5i. So the same thing is rearranged in x plus yi form. So finally we have the standard form. So the reason behind doing this type of multiplication is that previously we have I in the denominator. Our target should be removed I. Okay, we should have this one. Let us consider we have a complex number in denominator, 1 negative 2i. So we need to have the conjugate 1 positive 2i. By this, we can easily have a real number, only real number in denominator. You can see the denominator is just a real number. So now we can separate like x and y. So this one is also known as rationalizing. Okay. So these are the problems that you have to solve from week 1. So I have marked the problems from here. So you can go through these problems. Okay. And besides this, you can have a look on this first two videos, part 1, part 2. So these are well organized. You will get the entire idea. So thank you for your time.